Okay, so let's review back what the intermediate value theorem says. Now you already have this in your notes. Okay, this is the intermediate value theorem. But basically what this says that if f is a continuous function, and that's the most important thing about the intermediate value theorem is that we're talking about continuous functions, that if we have two values at a and b, we have f at a and f at b, and if it's continuous between those points, any point n that we choose in here, there's going to be a corresponding value between a and b that makes f at c equal n. Okay, so the immediate use of this is that if we have a function and we evaluate it at some point, let's say it's a negative, f at a is something negative, and then we have another f at b, and let's say that's positive, we know there's a root between them. And so if we keep on kind of guessing down and getting closer and closer, you can estimate what the roots are by using the intermediate value theorem. So there's a few exercises like that. If we are a little bit later in the semester, we're going to be going back to that again for that purpose. But anyway, so this is the intermediate value theorem. So last Wednesday, I spoke about the extreme value theorem. Now, here's another one that has the word value in it. But this talks about if f is a continuous function. So here we're still talking about continuous functions on a closed interval. So between a and b, then f attains an absolute maximum value f at c and an absolute minimum value f at d at some numbers c and d within this interval. Okay, so what this is saying that if we have a continuous function and if we have an endpoint that includes or if we have values, an interval that includes the endpoints, we're going to have both a minimum and a maximum value in there. And if you see it drawn out, it's probably not all that surprising that there's a minimum and maximum value. So here's a continuous function. Here's my points A and B, or here's a C and D that shows the maximum and minimum values. The A and B, of course, are the ends of the interval. And so here's another one where the minimum happens to be at the end point, the maximum somewhere in the middle. If we have a function that's not continuous, we're not guaranteed to have a minimum or maximum value. For instance, this function does not have a minimum value. The limit of the function is a small value, or is the smallest value in that function, but since it's not continuous there, that function doesn't actually have that value in it. Okay, so natural consequence of this is, or not a consequence, but kind of a useful extension of this is Fermat's theorem. And so we have a local minimum or maximum, and the derivative exists at that point. That derivative has to equal 0. Okay, so if I go back to what my graphs look like, so here's a local, or even in the global maximum, and here's the minimum. If these occur at C, and if we have and if the derivative exists, the derivative is going to be 0. And think about what the derivative says, that if the derivative is positive, that means you're increasing. If the derivative is negative, that means you're decreasing. So at some point, when you switch from increasing to decreasing, the derivative is 0. So think about that in terms of the intermediate value theorem applying to the derivative, right? If we go from a negative to a positive, that means we have to go through 0. And that 0, the derivative 0, is where the function's value is at its maximum. Same thing with the minimum. Am I saying things too fast? Okay. Then when a function's decreasing, you expect the derivative to be negative. When it turns around and it bottoms out and it starts to increase, then the derivative goes from negative to positive. So the intermediate value theorem says that if the derivative is continuous, we're going to have a derivative of 0. Now here's a function that we have a local minimum, but the derivative doesn't exist at a sharp point, right? There's not a single tangent line that fits there, and that's okay. This is really what Fermat's theorem is saying, is that if there's a local minimum and if the derivative exists, then the derivative is 0. So if you don't have a derivative, it doesn't equal anything, right? So we've defined a critical number as either this point where the derivative is 0, or if it doesn't exist, it's going to be the point where it doesn't exist. So if I go back to here, C1 is a critical value, C2 is a critical value, and here this C is also a critical value because our derivative does not exist. Okay, so if we reword Fermat's theorem, what it says is that if a function has a local or minimum or maximum at C, then C is a critical number. Okay, so Fermat's theorem, the way I defined it before, basically said that if it has a derivative, the derivative is 0. Here it is, a local minimum or maximum. If you have a local minimum or maximum, then if you have a derivative, it's going to be 0, so that makes it a critical point. If you don't have a derivative, that also makes it a derivative. That also makes it a critical point. So Fermat's theorem then comes down to this: that we look for where the derivative either equals 0 or does not exist, and those are the candidate spots for your minimums or maximums. Oops, I'm sorry, that was a little faster than I wanted. Any questions at this point? So we have 3 theorems so far I've talked about. The intermediate value theorem that says that the function has a value for x that will give you, or c, that f at c will be all the values in between the two values at the end. We have the extreme value theorem that says over closed intervals that there's going to be an extreme value either at the ends or at some point in the middle. And Fermat's theorem that basically says that if we have a local minimum or maximum, they're going to occur at C. Okay. Back in business. All right, everybody have your notes up to date this far? Okay, so let's actually find these absolute minimums and maximums that exist on a closed interval a to b. All right, so number one, what we have to do is find the values of the function at the critical numbers in the function. So the way we're going to find the critical numbers is we're going to take the derivative of our function and then set it to 0 and see if we can solve for it, or see what the domain is to see if we have any exclusions that are between a and b. Then what we need to do is compute what the values are at the endpoints. And so then what we do is then choose the largest and the smallest values, and that'll be the largest or smallest values in that interval. Okay, so let me give you an example here. So we want to find the absolute minimum and the absolute maximum for this function, x squared minus x, on this interval from -3 or -1 to 3. All right, so here's a continuous function. So all the things that we know about continuous function applies. And here's a closed interval. So the extreme value theorem applies to this because it's a closed interval on a continuous function. Okay, so what we do is first we take the derivative, and so we get 2x minus 1, and we set it equal to 0, and we find that the derivative equals 0 when x equals 1/2. And then what we do is we evaluate this thing, f at 1/2. If I just plug in a 1/2 here, I get 1/4 minus 1/2, which is -1/4. And then I'll plug in the endpoints. F at -1 is going to be 2. F at 3 is going to be 9 minus 3 is 6. Okay, so I have my 3 points. Now, my absolute mins or maxes will happen among those And so we look at the values and we say, oh, negative 1/4 is the minimum value, and the maximum value is at 6. Okay, so let me make a little graph on this. We know that f at x equals x times x minus 1, right? And so what we have is a parabola where the intercepts are at 1 and negative 1. And if we look at the original one, remember our axis of symmetry on a parabola is going to be at minus b over 2a, which in this case is minus a negative 1 over 2 times 1. So our axis of symmetry is going to be at 1/2. So here's my 1/2. This is 1. And that's 0. So my absolute minimum is going to be negative 1/4. So if this is 1, let's say this is 1/4. So this point here is my absolute minimum at f at 1/2 equals negative 1/4. And this function, I'm only interested from negative 1, which would be about here, and at negative 1 it's 2. So our function value is here. And then f at 3 is 6, which is probably way up here. And so I'm only interested in this if I were to just graph it, look something like that, from point to point. So the absolute minimum I found by the derivative, and the absolute maximum I found by evaluating the endpoints.
Okay, where did the point 0 come from? Is that f prime of f?
What point 0?
You have a point 0 on your graph. Did you get that from f prime of x equals 2x minus 1?
Oh, 0, 0?
Yeah.
Well, I know that when I factor it, I have my roots at 0 and at 1. Okay? So what I'm doing here is just illustrating what I found directly here. Okay? So all I wanted to do was make a graph, and so I plotted the roots to the graph. Yes?
To find f of 1/2 and f of negative 1 and f of 3, are you plugging it into 2x minus 1?
Yes. Not to 2x minus 1, I'm plugging it into the original function, x squared minus x. So let's look back and remind ourselves, what is the question here? The question is, we want to find the absolute minimum and maximum for this function on this closed interval. It's a continuous function. It has endpoints, so the extreme value theorem applies and Fermat's theorem applies, right? So we know that the extreme value is going to happen at either of the ends, or it's going to happen where the derivative is 0. And here we have a derivative that equals 0 at x equals 1/2, so we evaluate then the points where the 1/2 is a critical point, so we evaluate that. We evaluate the endpoints, and we choose which is the biggest and the smallest values. Okay, everybody up with that? Okay, let me throw out a couple for you here. So why don't you try these two? I want you to find the critical values only here. We're not looking at the extreme values, just the critical values. Okay, so there's your solutions. And so now what I want to do is I want to find the absolute max and min for these two functions on these intervals. Okay, so remember what the procedure is here. We find the critical values, we evaluate the function and the critical values within the intervals, and then we decide what are the largest and the smallest values. Now, one thing that you may find is that you may have more than one maximum value. It'll be the same number, right? It can only have one absolute maximum, but it may occur at two different places. So, for example, if we're talking about the just f at x equals x squared over the interval -1 to 1, both at -1 and 1, f at x equals 1. So those would be the maximum values. And so it's the same maximum occurring at two different places. So I'll let you work on these. So what we're going to do is first take the derivative. Okay, take the derivative of that, we get 54 minus 6x squared, and so I'm going to factor that fully, and so I get my critical values is where the derivative equals 0. And so where does this equal 0? It equals 0 at 3 and -3. So those are my two critical values. So now I have four values to look at. I have my two critical values, and I have my two endpoints. And so I want to evaluate f at those 4 points. And so f at 0, that's easy, that's just 5. F at 4, just plug in a 4 up here, and we get 93. We'll look at f at 3, because now we're evaluating the function at the critical point, and that's going to turn out to be 113. And f at -3 is -103. Okay, so what we have here is, here's the maximum, and here's the minimum. It has to be one of the four values that I'm picking. Okay, so if I were to, let me say, make a real quick graph of this, you know, what I have is f at 0 equals 5. So let's say this is 5 here. So I have this point. Now f at, oh, you know what? We have a little issue here, and I'll talk about this. Because this is actually wrong. Well, let me finish this. Okay, so we have at 4, which is our other endpoint, we have, what is that, 93, right? So that's way up here, 93. Now, f at 3 is 113, so that's way up here. So however the function goes, it might go something like this. Okay, this is the maximum value, and this is the minimum value. So I messed up here. It's not -103. Anybody tell me why not? Why is that not the minimum value of the function on the interval? Okay, so what we do is we exclude -3 because it's not inside the interval. We're only interested from 0 to 4. So we find the critical value at -3, but we don't care because it's not within the interval. So of the 3 remaining ones that I choose the minimum value, and so then that equals and there's the minimum value. So my maximum value, minimum value, the other endpoint, f at 4, is somewhere in the middle. Okay, so just to kind of recap, sorry for the the misdirection on the -3. I have my function. It's a continuous function because it's a polynomial. I have this interval from 0 to 4. It includes the endpoints. So here I have my derivative. I just take the derivative. You know how to do that. And then I'm going to fully factor it so I can see where my roots are. So where my derivative is 0 is where the derivative is going to look like this. So it's going to be either the maximum or minimum value, because it's either going to turn around like this or turn around like that. So those are my critical points. I discard this critical point because it's not in the interval that I'm interested in. And so these other 3 points, what I do is I evaluate f at 0, f at 4, and f at 3. And between the 3 of those values, the biggest one is 113, the smallest value is 5. All right? Shall I do the next one too? Okay, so oh look, I guess I didn't step through that one already. So we take the derivative, and so we use the chain rule here, right? So we take the derivative of the outer function, which is the cube, and so that's 3 and then squared, then take the derivative of the inner function, which is 2x, and so multiply all that out, and I get 6x times x squared minus 1 squared. Now I can get this by inspection, right? I know that 0 gives me a 0 on my derivative, and then x squared minus 1, I know how that factors. That's going to be x equals 1 and x equals negative 1. So here are my 3 critical values. So then I'm going to take my, all of these are within my interval, so I'm going to evaluate all of them. F at negative 1 is going to be 0. Okay, so negative 1 makes 1, so we have 0. F at 0 is going to be negative 1, because that's just 0 minus 1 cubed, is negative 1. F at 1 is also going to be 0. And then F at 2, so we have 4 minus 1 is 3. 3 cubed is 27. So here are the values that I have for my function. And so my smallest value is going to be this. The largest value is going to be that. And so this one occurs somewhere in the middle of the interval. This one occurs at the end of the interval. Okay, any questions on this? So, yes?
So if you got like -2, that wouldn't be inside.
Yeah, if I found one of my derivatives is 0 at -2, discard it. Okay, so it's very procedural here. What you do is you first check to see about, what the interval is, take the function, take the derivative, see where the derivative equals 0, or see where the derivative does not exist, right? Because that's going to be a critical point as well, and then evaluate it. Okay, so this is all nice and well and kind of esoteric. So here's a question that you might come across. So you have some cardboard. You're actually a packaging engineer, and there are such things as packaging engineers. They design boxes, right? And so what they need to do is they need to make a square bottom box with no top that's made from 27 square feet. That should be square feet, not cubic feet. Let me see if I correct that. Yep, there it is. Square feet of cardboard, and has the maximum volume. Okay, so I have a piece of cardboard that I'm going to use, and I'm not going to count the waste by cutting out the corners, but I'm going to make a box that has 27 square feet of cardboard in it. What's the maximum volume that I can get out of this thing with a square bottom? Okay, so let's think about this. What I can do is I can develop I can write the formula for the volume of the box with respect to the length of, the length of the side and the bottom. And then I can calculate the square footage, and I can see what is, where does the maximum volume happen, and how much does that translate into for the cardboard to be used. So let me march through it. Okay, so I'm going to define B as the size of the bottom, that's the length, and H is the size of the side. So with the B and H, we have both the height, and since it's a square bottom, we have B times B is the area of the bottom. So the area that we're going to use is 27, so that's going to be the bottom squared plus the 4 sides that are the bottom times the height. Okay, so if I draw a picture, I have a box. It's open on the top. I guess you can see that. So the bottom is B, and the height is H, not S. So if I look on the area of the side, that's B times H, and I have 4 of them, so I'm going to make that 4BH. And then the bottom is going to be, if I look at this thing down here, it's going to be B times B, so B squared. Okay, so here's the volume, then. The volume is B squared H. All right. we know we want the area to be 27 square feet, so I'm going to set 27 minus b squared equals 4bh, and here I have a b squared as well, so I can make this substitution, or actually I'm still working here, I can divide this both sides by 4b, and so I get an expression in h. Okay, so I know my 27 square feet, and then I use b as my independent variable, like how big should the bottom be, and once I decide the bottom, I get the height out of it. So what I'm going to do here is, since the volume is b squared h, I'm going to put in b squared plus, or times the height, and so if I expand all this, I get 27b minus b cubed over 4. So here's a formula for the volume that only depends on b. Okay? Everybody follow this? This is just algebra here, where I'm saying from the size I get this formula, I can solve for h, and then I can stick the h in this volume formula, so I know here's the formula for my volume based on using 27 square feet of cardboard. Okay, so how do I find the maximum volume? Okay, the maximum volume is going to be where the derivative of the volume equals 0. Okay, so I'm going to take the derivative, split this into two terms, 27b over 4 minus b cubed. And if I take the derivative then, the 27b over 4's derivative is just 27 over 4. Derivative of negative b cubed over 4 is going to be 3/4 b squared. And so I'm going to set that equal to 0, and then multiply through by 4, and then I get b squared equals 9, so b equals 3. Actually, it's plus or minus 3, but I'm not going to have a negative dimension. So I know that if my box has a base of 3, and then I'm going to go back up to my height formula, I can find the height of this thing as 1.5 feet tall by 3 feet on each edge on the bottom. That's the maximum volume that I can get with that piece of cardboard. Okay.
Are we gonna have to do that on
Yeah, this is calculus. Calculus, the point of calculus is to calculate. So those of you that, well, very few of you have actually taken Math 12 from me, but you can see the way that I teach a word problem is all included here. All right, I drew my picture here. I probably should have drew it on the solution here just to illustrate it, but notice I defined variables, and then I set up my equations, solved the equations, and then I answered the question the way you would if somebody asked you that question. Okay, it's not going to be sufficient just to walk up to somebody and say, if somebody asked me that question, D equals 25. That's irrelevant. If the question is, what's the maximum, what are the dimensions of the maximum area, you'd say it has to be 50 wide and 25 deep. So I'm going to be looking for this as you do word problems. Defining your variables carefully, coming up with the relationships between the variables and the things that you know, then do all the solution, and then answer the question. Okay, so if you remember two things, define variables and answer in a plain English question, that'll help you a lot to frame these kinds of word problems, or any kind of word problem actually. Okay, so let's look at what derivatives will tell us about the shape of the curve more than this. Okay, so we know already that when the derivative equals 0, we have the maximum and the minimum values. Let's look at what the derivatives will tell us beyond that. So the thing that you want to do is go back through your pre-calculus book. I think section 28 probably refers to Stewart's text, but look back into what we've done in terms of characterizing functions. How do curves go, where the asymptotes are, long-term behavior, and all that. So all of that stuff is going to come into play here. And we are going to now add some theorems, and we're going to define these things as tests that we do to characterize some of our theorems. Okay, so the first one is, let's look at, just step back and look at a function. And what does this mean when f at x is greater than 0 or f at x is less than 0? That just means when's the function positive and negative. We're going to get into tests, the tests with derivatives and the second derivative, where we're going to be looking at when is it positive and negative. But I want to first review how do we get to the negative and positive values of the function. Okay, remember we did that to a certain extent before. So let's say we have this polynomial here. And I want to find the areas where is this function positive and where is it negative. So the first step is, let me factor it. I notice I have an x all the way through it, so I can at least factor that out, but I also notice there's a bunch of 3's and 6's, so I can factor out a 3x. Then I have x squared minus x minus 2, so that factors with these three intervals. Okay, so we know then that f at x equals 0 at x equals, or yeah, f at x equals 0 when x equals 0, x equals negative 1, and x equals 2. Okay, so let's look at these values here. Why do you suppose these are not coordinates, these are intervals. Why do you suppose we look at these intervals now? Think in terms of the intermediate value theorem. And, yeah, it's continuous, and so it's going to go from positive to negative. That's what we're trying to find out. And so it's going to go through 0 to go from positive to negative. So the only time it's going to switch from negative to positive is when it goes through 0, and it goes through 0 at the roots. Okay? So, and that's the intermediate value theorem that tells you that when you have something positive and it goes to something negative, it's going to go through 0 for a continuous function. Okay, so I'm going to set up the intervals that I'm interested in. I'm going to go up to the lowest root, go from the lowest root to the next root, go from that root to the next root, and then from the last root up to infinity. And so I'm going to list my factors. And then all I have to do is, somewhere in this interval, what are these things? Are they going to be positive or negative? All right, so 3x is going to be negative when we're less than 0, and it's going to be positive when we're greater than 0. Right? That factor, when it's in there, it's going to give us a negative sign when we're less than 0. X plus 1 is only going to be negative when we're at this negative infinity to negative 1, right? Because if we get over that, like let's say in the middle of this one, negative 1/2, we're going to have this end up to be positive 1/2. So this factor is negative in this interval, but it's positive for all the other intervals. Okay, so then let's look at x plus, or x minus 2. Okay, at x minus 2, anything below 2, it's going to be negative. So this is below 2, so this is going to be negative here, right? Because if we put a 1 in here, we get 1 minus 2 is negative 1. And so the only time this is going to be positive is if x is above 2. So we can make the list of our signs. And then when we add up how these factors will multiply, we know, is the function going to be positive or negative? Positive, negative, or negative, negative, negative. If we multiply 3 negatives, we get our function is negative. Negative, positive, negative, that's a positive number, so it's going to be greater than. So it's going to be above and below our intervals. We've done this before, right? Is it shaking loose some cobwebs? So this is just the kind of analysis that says, when we have a function, when is this positive, when is it negative? Okay, so I'd like you to try this one and then we'll end here. Okay, where is this positive and where is it negative? Okay, I see a lot of you have finished the table and figured out where f at x goes. So first thing we do is we factor it. And now we have a name for the values that make this thing, well, no, we're not talking about the derivative, so I take that back. So we factor this and we know what values will either give us f at x equals 0 or where f at x is not defined. Okay, so remember where we have in the denominator, that's an asymptote, so it's possible to go from positive to negative if the short-term behavior goes off to positive infinity and then comes from negative infinity. So we have to treat that separately. So we look at these values. And we set up our table of intervals where they're bound by these values that we found. So we go up to -2, then from 2 to -1, -1 to 1, and then 1 to infinity. And then we list out all our factors and we decide when are they positive and when are they negative. Okay, and then we can see when is it less than 0, when is it greater than 0. So between negative infinity and -2, it's less than infinity, or less than 0. -2 to -1, it's actually positive, then it's negative here, and then positive there. Now it's possible that you have two intervals so they don't alternate, and we'll see when that happens with some graphs that we'll actually draw next week. So so that's it for today.